Yeah, and since all of these cubes put together makes a 4 by 4 by 4, then it was easy to make a cube to hold them all, such as this, because you know that it would be 4 across, 4 up, and a depth of 4.
Yeah, like when I was talking about this one, when you see how things fit inside of each other, when we were putting them together, you would have to understand how these would like go out and stuff, and how each pentacube would fit together, like we do in posters and stuff, and that would help us with the placement of the polyhedrons inside cubes and stuff.
What activity did you find that was the most productive in the making of the cube? The drawing and the assembly of the cubes, the assembly with the Linka cubes, and making the 4 by 4 by 4.
What?
Which one did you find most productive?
I think you should read it for us.
I think we should.
Sounds better.
Because
Yeah.
we can't just like magically know it.
Okay, well,
Mr. Koch, you read, and then so we can answer.
I don't know always when you guys are finished, but what,
Yeah, but once we start getting stuck, like right about then you should. And I'm the only person talking. I talk so much.
I mean, the thing is that we're not going to be using the questions really. We'll be using.
Yeah, so but
It's hard for us to get the answers when none of us know what we're doing.
Yeah, because when you raised that question, it was easiest for us. We just jumped in.
Okay, so
All right, so
we'll continue on.
I was going to do that anyway if I thought of questions to ask that I thought would, make you keep going on.
I'm continue that that way. Just remember, stay loud.
Okay, I'm loud. No one's loud. No one was
I can be loud.
My name is no.
Alright, you can be loud. Talk the way I am. It's loud, it's clear, it'll be heard.
No, it's not.
Yeah, it's really not.
Right? Alright. In 5, 4, 3.
Which part of these threefold activities, drawing the assembly of the cubes, the assembly with the Linko cubes, or the making of your own 4 by 4 cube, did you find the most productive?
I think drawing.
Drawing. Yeah.
Because it was actually the most difficult, because you had to think of a 3-dimensional thing
On a
and
2-dimensional
put it on a
plane.
2-dimensional plane.
Yeah. See, when you get practice in a harder way, then you can understand the more difficult stuff easier.
Right. Gives you a better understanding of.
That
Gives
makes
you
no
like
sense.
It gives you like a foundation for you to build on.
Yeah. Because when we were drawing on the 2-dimensional things, we incorporated everything. We were talking about the planes, the views, the whole putting together of everything. And it's really good.
I also thought that the drawing was the most productive because with the 3-dimensional cubes, I don't know, I found it very easy to put them together.
Yeah.
You know? But it was more with like the views. It was harder to imagine the view, and when you learned it, it was like I felt like I was learning more.
Has to do with architecture.
Yeah. And even from a step up from working on the dot paper to then working on like plain paper, that was hard. That was really hard because you had to do the measuring also with the planes and stuff.
Did drawing the views of the cubes, of your 4 by 4 cubes, remind you of anything from the real world? Like your picture across the back there? Have you ever tried to put something together like a bicycle or?
No.
You ever buy something? You have to put
Like the
together?
steps from.
Right, you have to see the view.
Not really.
No? You have to see the relationship between this and the...
Did you ever have one of those built a skeleton or something?
Putting your...
Oh, I put together a heart once, but it was really nothing like this.
Yeah.
Because we made our own steps in this. Like, we had to figure out where everything went. And a lot of kits and stuff that you get at stores, it tells you where to put everything. So this is actually a lot more difficult.
Yeah. I mean, your drawing up there of the assembly of the 4 by 4 by 4 is like when you would buy a model or like a plastic model.
And
But those would be the instructions.
Yeah, well, that's what you have there, instructions.
Yeah, we made our own instructions to make a 4 by 4 by 4.
Yeah, I think that was the hardest part, making the instructions, not actually doing it.
Yeah.
Like figuring out which way to put them, not actually physically putting them together.
Right. Being able to show somebody else how to do it.
Yeah.
Yeah.
How would you complete different parts of the projects differently if you could do it again? What would you do differently?
Well, I think we have more experience now, so we'd be able to.
What would you do?
I might have done working with the Linka cubes first and then drawing, because if you like play with the three-dimensional things for a while, then you visualize it really, like, it's easier to visualize it, and then you could draw it, and then you could still learn from the drawing, and then you could go back to building it.
I don't think I would do so many like activities in the workbooks, because after a while it got kind of monotonous, and you understand it. It's not like a hard concept to grasp. So.
Yeah, I thought we should have done more three-dimensional activities and less two-dimensional activities. I thought I had understood the two-dimensional after a while, but I thought we could have done more with the like.
It was important to do the two-dimensional, but still,
I think
like
it was too
after a
much.
while, yeah.
And in the end, the final project.
These are the Platonic solids, named after the ancient Greek philosopher Plato. The simplest regular polygon is the equilateral triangle. How can equilateral triangles fit together to form corner pieces of Platonic solids? 3 triangles can form a corner, and 1 more triangle closes the shape, forming a Platonic solid with triangular faces. This solid is called a regular tetrahedron. 4 triangles meeting at a vertex form a corner that looks like a pyramid. 2 of these corners can join to form a Platonic solid with 8 triangular faces. Notice that all the corners are identical. This solid is called a regular octahedron. 5 triangles meeting at a vertex form a shallow dome. Joining 2 of these domes will not form a Platonic solid because not all of the corners are the same. Joining the 2 domes to a center band of 10 congruent triangles forms a Platonic solid with 20 faces. It is called the regular icosahedron.
In preparation for the polyhedron unit, students learn Euclidean constructions, including such fundamentals as perpendicular bisectors, parallel lines, angle bisectors, altitudes, and medians. This aspect of the curriculum leads to the construction of triangles, quadrilaterals, and polygons from multiple approaches. Students share these approaches in many mini-project tasks. This leads to the study of area, surface area, and volume. Algorithms become an integral part of the study of area since students implement algebraic concepts. The understanding of tessellation geometry leads to the study of Platonic solids. Students learn the importance of templates in the construction of Platonic solids. At this point, students construct the nets for the solids, including truncated solids, both open and closed, as well as snub solids and rhombic solids. Finally, students are introduced to the Space Labyrinth project. They design their own open or closed packed 3-dimensional tessellation. Students are encouraged to work in groups since the project requires assembling of multiple replications of the same solid. Again, templates are made and used to maintain uniformity of size.
And the icosahedron.
My goal as a math teacher is to teach for understanding, making learning a long-term thinking-centered process. As a guide and facilitator, I want to develop ways for students to think about math and help them acquire and construct knowledge about math. When students can explain and simplify, find evidence and examples, make analogies, and apply concepts, they then truly understand the material presented. My aim is to have my classroom as student-centered as possible, to maximize student involvement so that many activities are student-directed and designed. Hands-on projects using manipulatives and computers form the core of my curriculum. Students are encouraged to discover and create. Student-based inquiry leads to successful problem solving because students construct or dismantle objects, measure and record their observations, verify and predict outcomes, and ultimately come to their own conclusions. This discovery process makes math issues believable and at the same time empowers students as they take ownership of mathematical concepts. While implementing the Krista McCullough Fellowship this past year, I have had the opportunity of documenting my students' progress and networking the techniques and curricula I developed over the past 5 years to other educators, parents, and administrators through this video. My large classroom is arranged so that the hands-on curriculum can be easily implemented. Sets of student tables face each other so that cooperative work is easily arranged among the 4 to 6 students seated together. Completed and painted polyhedrons hang from several clotheslines which span the width of the room. Displays of geometric sculptures and architectural models provide additional visual motivation. I have installed magnetic boards on several walls. Use of these special boards allows for further demonstration of math theories such as transformational geometry. Students can also use these magnetic boards to solve problems independently. Traditional math tools such as rulers, compasses, and protractors used in Euclidean geometry are coupled with templates, polyhedron nets, mat knives, glue guns, foam core, paint, plexiglass cutters, and plexiglass. Student constructions range from painted oak-tag models to sophisticated multicolored plexiglass renditions. The computer lab complements these activities. I believe that my teaching meets the needs of my students because it offers them alternate approaches for successful performance. Making math connections motivates students and empowers both the girls and the boys by increasing their math abilities. Middle school students need to strengthen their higher-level thinking skills. Hands-on manipulative projects enable them to understand spatial relationships while they discover techniques for creating three-dimensional models. Much of this work is done collaboratively. As they work on these projects, students of all levels are engaged, empowered, fascinated, and ultimately successful. From the American Educator, Fall 1993, Teaching for Understanding by David Perkins. At the heart of Teaching for Understanding lies a very basic question. What is understanding? Ponder this query for a moment and you will realize that good answers are not obvious. To draw a comparison, we all have a reasonable conception of what knowing is. When a student knows something, the student can bring it forth upon call, tell us the knowledge or demonstrate the skill. But understanding something is a more subtle matter. A student might be able to regurgitate reams of facts and demonstrate routine skills with very little understanding. Somehow, understanding goes beyond knowing. But how? Clues can be found in this fantasy. Imagine a snowball fight in space. half a dozen astronauts in